Okay, today we are going to talk about the ideal gas law as well as gas stoichiometry. Okay, ideal gas law and the combined law are two others, again, that we saw last year. Here is the combined gas law, and the only difference that's on this one that we didn't see last year is they also add in the Avogadro's piece, which it's like anything else. If they don't tell you that you're changing Avogadro's number, then you don't have to worry about including it. You can still just use P1V1 over T1 equals P2V2 over T2. Then you've got the ideal gas law, okay, and this is PV equals nRT, and for R, this is the ideal gas law constant, and there are a couple of different versions of R depending on the units that you're dealing with. For this particular equation, it's always going to be 0.08206 liters times ATMs over moles times Kelvin. You may also see this as 0.0821. I'm pretty sure it's on the AP Chem sheet, but I can't remember which one's on there. We're going to come to some spots where we also have to use another version, which is 8.314 joules over moles times Kelvin, and that's just when you're dealing with joules in your units. And remember, for the ideal gas law, you always have to have them in these units. It has to be liters, ATMs, moles, and Kelvin for all of these. Okay, real gases versus ideal gases, and we'll come back to this at the end of the unit as well. But an ideal gas really is just a hypothetical substance that obeys the ideal gas law. It's a perfect situation that makes things easier to study. And real gases can approach this behavior the closest at very, very, very low temperature and very, very, very low pressure and very high temperature. And those are going to be scenarios that are going to allow for gases to have the most movement, the fastest movement, and the least amount of attraction forces between them. So that's why. We're going to deal more with this in 5.6, and also in your notes there is an ideal gas law sample problems. Look through page 199 to 202. I didn't want to waste time doing those right now, but anywhere from page 199 to 202, because it's pretty strict plug and chug. Okay, now we're going to talk about gas stoichiometry. Now, it's still stoichiometry, which means that we still are going to need and look at the ratios between a balanced chemical equation. And we still can have to go from moles to moles for all these balanced chemical equations. The difference is going to be how do we get 2 moles, because a lot of times when we're dealing with gases, they don't give us nice pretty grams. But you still can absolutely still use your chart or your mole ratios and dimensional analysis, whatever works for you. Now, here's one of those ways. If something is at standard temperature and pressure, okay, which is 0 degrees Celsius and 1 atm, there's automatically 22.42 liters per mole. Again, some sources will show 22.4. Either one is fine. That's why you get plus or minus sig figs on your final answer. All right, now just to show you molar volumes for various gases at 0 degrees Celsius. It doesn't matter what substance you're dealing with, we're going to, even though there's some variability here, we're going to go ahead and say, and when we say molar volumes, we mean 1 mole of the substance. Okay, but we're going to use 22.4 as a standard, and that's one of the ways you can get from liters to moles so that you can then do your stoichiometry problem. Okay, and that's when it's nice. When it's at standard temperature and pressure, you're golden. The other way, when it's not at standard temperature and pressure, is to use PV equals nRT. Because if it's not at standard temperature and pressure, they're going to have to give you the temperature, they're going to have to give you the pressure, they'll either give you the volume and you have to find the moles, or you may have to find the moles and then ultimately convert it to volume. So these two things right here, just like with molarity, we had to get into our mind that that's how we could go from liters to moles. These are your tickets on gas law stoichiometry. And this picture just shows up all the time, so I don't know why I keep showing it, but haven't found another better one. All right, let's do a couple of samples on these. Okay, calcium oxide is made from the decomposition of calcium carbonate. We got to find the volume of carbon dioxide at STP made from the decomposition of 152 grams of calcium carbonate. Okay. What do they tell me? They tell me I'm at standard temperature and pressure. That makes me happy because that means I can use my 22.4. Pen is not working, so I'm trying to do this with the mouse. 22.4 liters to go to moles, and I've got the decomp of calcium carbonate. All right, so first here's my balanced chemical reaction. Calcium carbonate is going to decomp into calcium oxide as well as carbon dioxide. It's all a 1-to-1, which makes life pretty, and I'm given grams of calcium carbonate and I need to get to ultimately to volume of carbon dioxide. Now, I'm going to show you dimensional analysis. If you wanted to do the chart, you still could do grams, molar mass, moles, change, and X, and ultimately get to moles of carbon dioxide, and then use your STP to go from moles to liters. Another way to do it is what's going to pop up here. Let me get rid of all this writing. If I start with 152 grams of calcium carbonate, I'm going to go to moles, still by dividing it by the molar mass, so it's not really that different. That's going to get rid of the grams unit there. Then I got to go from moles to moles. It's a 1-to-1, so it's not going to change it, but that would be the same as with the chart. And then finally I got to multiply it by 22.42, 3 sig figs in my data, so 34.1 liters of carbon dioxide. It's not drastically different. Just like molarity, with the curveball was molarity in solution stoich, gas stoichiometry, it's figuring out how to get from liters to moles. Okay, sample of methane gas having a volume of 2.80 liters at 25 degrees Celsius and 1.65 atm. So right off the bat, it's not at STP. So we're going to have to do something a little different. And was mixed with a sample of oxygen gas having a volume of 35.0 liters at 31 degrees Celsius and 1.25 atm. Mixture formed carbon dioxide and water. It's a combustion of a hydrocarbon, so we should have been able to predict those products anyway. Find the volume of carbon dioxide at 2.50 atms in 125 degrees Celsius. Okay, so a couple of things that we have to do. They give us amounts of everything. Now here's our balanced chemical equation. They do give us amounts of everything. They give us amounts of methane at a certain temp, and they also give us amounts of oxygen at a certain temp. So off the bat, we got to figure out what is the limiter. All right, now the other thing is that we want to find the volume of carbon dioxide at 2.50 atms and 125 degrees Celsius. So ultimately what we need to do is get everything to moles, do our stoichiometry, and then at the very end we're going to do PV equals nRT to figure out however many moles that would be what the volume is. Okay, so here's our limiting reactant. Well, if we've got methane and we've got oxygen, I've just rearranged the equation so that we can solve for moles. They gave us pressure and volume of methane. My moles would be 0.189. They gave me pressure and volume and temperature of oxygen, and I would have 1.75 moles. Now at this point you absolutely could take this and plug it right into your chart of moles, change, and X. Honestly, it's whatever you want to do here, and you'd still have your balanced chemical reaction. We would still be going for moles of carbon dioxide. Now, the other way is, and one way to do this is if you convert one reactant to the other. So for example, if I had 0.189 moles of methane and I figure out how much oxygen I would need, well, if I had 0.189 moles of methane, my 2-to-1 from the balanced chemical equation, I would need 0.378 moles of oxygen. Okay, well, here's my O2. I have plenty of O2. So that means that my methane is going to be my limiting reactant. Okay, so however you want to do it, but my methane is going to be my limiting reactant. Alright, so then the last part here, okay, when those pop up, cross those off because clearly those are wrong. I should have taken those off of your this should say, or just switch it, that methane is your limiting reactant and that O2 is your excess reactant. Sorry about that. Just so we're getting to understand it. Alright, so flip-flop those and fix those for me, please. Alright, now we got to find the amount of product produced. So we start with the methane, or we just go right to moles of carbon dioxide, depending on how we want to do that. That red is kind of funky. Let's change that here. Nope. Ink color. Let's just go with good old black. Alright, now once we have the moles of carbon dioxide, excuse me, they had given us a temperature and a pressure, and we needed to find the volume. So we go back to PV equals nRT, we plug and chug, we get 2.47 liters of carbon dioxide. Now remember, the only two things that are going to be different with gas stoichiometry are either the ideal gas law or our ideal gas constant, where they've essentially just done the math for you, where it's 22.4 liters per mole if it's at standard temperature and pressure. And if you don't want to memorize this, if this doesn't make sense, even if it's at standard temperature and pressure, you can still use the ideal gas law. You just plug and chug in 1 atm and 273 Kelvin. So however you want to do that. Okay, here's taking things to the next step a little bit. This is the accept the proof version. This is a way to find molar mass and density in the same problem. And here's all the proof. Here's your molar mass. Here's your ideal gas law. We're going to start to substitute in some things here. And ultimately, take home message. If you want the algebra, there it is. Or know that this is another equation we can use where capital M is molar mass, D is density, R is the ideal gas constant, T is temperature, and P is pressure. So how might we see that? Well, there's a sample on page 206. It says if the density of a sample of a gas is 1.95 grams per liter at 1.50 atm and 27 degrees Celsius, find the molar mass of that gas and identify what the gas would be. Okay, so it's simple plug and chug. We're still dealing with our regular ideal gas constant, not as opposed to the one that has joules in it. All right, we're still converting Celsius to Kelvin. It's just a new equation where our molar mass is going to be 32.0 grams per mole, and I know you have the answer, but I really hope that most of us could get that it would be oxygen. Okay, so don't get freaked out with gas stoich, ideal gas law, or using your conversion at standard temperature and pressure. Okay, good luck. Hope that helps.